Let's look at the consequences of connecting resistors in series and parallel. Say we have a voltage source V, which is connected across two resistors R1 and R2 in series as shown. Let's say there is a current I going through the resistors as shown. I can apply KVL in the loop, starting at this point, coming back at this point, going clockwise. The statement of the KVL says sum of all voltage drops is 0. So when I go up, the voltage drop is negative V. And on the right hand side, I have voltage drop of I times R1 plus I times R2. That should be equal to 0. This implies my current I is equal to V over R1 plus R2. Now I want to find out what are the voltages here across VR1 and VR2. Well, VR1 is the voltage across R1, VR2 is the voltage across R2. So again, I just use the Ohm's law. So VR1 from top to bottom would be equal to I times R1, which will give me R1 divided by R1 plus R2 times total voltage V, and VR2 is equal to I times R2, which will be equal to R2 divided by R1 plus R2 times V. If you observe these formulas, what you see is the voltage across R1 is proportional to R1, and the voltage across R2 is proportional to R2. That means the voltage divides proportionally to the resistance values. And this is the so-called voltage divider. We can extend the voltage divider formulas to n resistors in series instead of just 2. So in this circuit, let me apply my KVL again, assuming current I going from top to bottom through the resistors. Then if I apply KVL, I will proceed similarly to the above example, and I get this equation here. And then I get my total current as the voltage divided by R1 plus R2 so on until Rn, which makes sense because when you connect resistors in series, the total resistance is just the sum of all the resistors, and therefore the current in the circuit we know should be V over the total resistance, and that is what we have. If I want to find voltage across the kth resistance, let's say Rk, that should be equal to I times Rk, which should be equal to Rk divided by R1 plus so on until Rn times V. So what this tells me again is when I have n resistors in series, then the voltage again divides proportionally to the resistance values, right? Note that if you add up all these proportional values, it sums up to 1. So that means you can extend the voltage divider to n resistors. So now let's look at current division. Let's say I have a current source connected parallelly or connected parallel to two parallel resistors R1 and R2. Let's assume there's current I1 through R1 and I2 through R2. Since R1 and R2 are parallel, the voltage across them will be the same, which means I1 R1 should be equal to I2 R2 according to Ohm's law. Now, if I apply a KCL at that node, I get I is equal to I1 plus I2. I can substitute for I2 in here, and I get this equation, which means I1 is R2 divided by R1 plus R2 times I. Note that in this case, the current through I1 is proportional to R2, and the current through R2 will be proportional to R1. That means I2 will be equal to R1 divided by R1 plus R2 times I. So what does this mean? It means that if R2 is very high, then more current will go through R1, and if R1 is very high, more current will go through R2. Right? So this is your famous intuition which you have, which says current goes through the path of least resistance. Now, that particular statement is not completely accurate because, let's say, if R1 is 1 ohm and R2 is 2 ohm, the path through R1 will be the path of least resistance, but the entire current won't go through R1. Okay, so the statement which says current flows to the path of least resistance is not completely accurate. It's just proportional, right? So there. So anyway, so that's the current division across two resistors in parallel. So these are the two. So the voltage division and current division are the uh, two different sort of things which you will see very often in many circuits, and that's why we make a special focus on those things.